Swayam Prabha. Digital India. Educated India.
In this lesson, we will look at some example problems in which you could exploit reciprocity of resistive networks. In general, if you are told that some network consists only of resistors, reciprocity is one of the things you should think about. It is not that every problem involving resistive circuits exploits reciprocity, but that is one of the things that is possible. Okay. There are many other things that are implied by having a network which has only resistors. Okay. For instance, if a network has only resistors, it means that it will only dissipate power and so on. Okay. So, there are many things that are implied by having a purely resistive network. One such thing is reciprocity. Okay. Firstly, you could be given a straightforward 2-port style question. So, let us say you would be asked, I apply 5 volts here and I see 2 volts over there. Okay. Then if I apply 10 milliamps over here to port 2, what current will I see? That way. Okay. So, this is a straightforward reciprocity problem, and you can think of the G parameter equivalent for this, because from this part, from the first circuit, you see that G21 is 2 volts by 5 volts, which is basically 0.4, and the second part is implicitly asking for G12. Okay, you apply a current to port 2, measure the current in port 1, and you know that for a reciprocal network, G12 is minus G21 is minus 0.4. So, I1 in this direction, which is the direction we take for currents in a 2 port. Okay. So, if this is 10 milliamperes, that is, if I use my old notation, I2 hat is 10 milliamperes, I1 hat will be G12 times 10 milliamperes, which is minus 4 milliampere. Now, this Ix is opposite of I1 hat. So, the answer is that Ix is 4 milliampere. Okay. So, this is one such thing, right. This is a very simple problem where you can exploit reciprocity. And things could get slightly more complicated. For instance, you could connect some things to the network. Okay. So, let us say I have 5 volts, 1 kilo ohm, and here also I have some resistor 2 kilo ohm. Okay. And let us say here I have 1 milliamp flowing. Okay. And then let us say you are asked this question, I apply 10 volts over there, what is the voltage drop across this 1 kilo ohm resistor. Okay. Now, this looks slightly more complicated. Now, one thing you can of course do is, because this is a resistive network, you can describe it with a 2-port parameter set, whichever it is, and apply the reciprocity constraint, that is Y12 equals Y21 or Z12 equals Z21 and so on. Okay. Now, the better thing to do is to realize that this is exactly the same problem as before in slight disguise. Okay. I will define my new 2-port to be something like that. Okay. This is A and A prime, that is one of the ports, and this is B and B prime, that is the second port, and that is terminated in a short circuit. Okay. And again I will take the exact same two port here. I have to take the same thing that I took earlier, okay, where originally we had a short circuit, we have now a voltage source, and this makes sense. Basically, we get this by reducing this voltage source to 0. Okay. You are not allowed to change the network, but you can change the values of the independent sources, right, in all these problems. When you set a voltage source to 0, it becomes a short circuit. Now, you can't apply reciprocity after changing the network. You should keep the network exactly the same. Okay. So, now you can think of whatever is enclosed within blue stuff as the inside part does not change at all. It is only the sources that are applied outside that change. Here on port A we apply 5 volts, port B is terminated with a short circuit. Here port B we have applied 10 volts and port A is terminated by a short circuit. Okay. Now, clearly this scenario where this side we apply a voltage, that side a short circuit, corresponds to Y parameter definitions, right. So, now what is Y21 of this circuit? It is, remember, for 2 port definitions, current IB, let me show it here, IB is defined that way, okay, if B is over there, and this is VA applied to port A, and Y21 is nothing but IB by VA, which is minus 1 milliamp by 5 volts, okay, because this 1 milliamp is in the opposite direction to the definition of IB. Now, what do we have in the other case? I have VB hat, which is 10 volts, and what I was asked to find was the voltage drop in this resistor, okay, that we know is related to the current through this short circuit. So, I will find IA hat. Okay. So, again that is the direction with which we define the 2 port currents. So, we know that IA hat by VB hat is basically Y12 of this network, which of course is the same as Y21, and that is given by minus 1 milliamp by 5 volts. So, IA hat itself will be this number times VB hat, which is 10 volts. Okay. So, that means that I get IA hat to be minus 2 milliamperes. Now, the voltage that I want, this voltage is nothing but minus IA hat times this resistor, which is 5 kilo ohms. Okay. If I call that Vx, my final solution is Vx is minus IA hat times 1 kilo ohm, which is given by 2 volts. Okay. So, that is plus 2 volts. This voltage drop here is plus 2 volts. Okay. So, here there is something that looks like a 2 port and you have some stuff outside it, but you define your own new 2 port and you can answer questions. Okay. Now, exactly in the same spirit would be, instead of connecting a voltage source here, I could connect a current source across this 2 kilo ohm resistor and so on. Okay. So, that is another possibility. Now, of course, you could be given problems that do not say anything about a 2 port network. Okay. So, let us try one such thing. Now, all of these, right, there are many ways to solve the problem. Okay. There are many ways to do circuit analysis. You should be familiar with a large number of ways, so that you can attack the same problem in multiple ways, and that is how you also build intuition. Okay. Now, as you go to more and more complicated circuits, some techniques turn out to be easier than others. So, you should really have an arsenal of all possible techniques. Okay. Now, this problem some of you may already be familiar with. Let us say I have V1, R1, V2, R2, V3, R3, and I am required to find the voltage here. Let me call this V x. Okay. How do you find it? Of course, you can apply regular circuit analysis and find it, right. Now, just for the heck of it, I will use reciprocity to do this. Okay. So, what do I do for that? Essentially, I should imagine that I have only one of these sources. I can find V x due to that one, and then I repeat it for other sources and apply superposition. Now, when I have only one of these sources and I am trying to find this, for instance, now I have the same circuit with V 2 set to 0 and V 3 set to 0. Okay. So, I can apply superposition and do this. I can also calculate V x in this case, and it is not very difficult, but like I said, we are discussing reciprocity. So, let us do it using reciprocity relationships. Okay. So, now I know that if I apply V 1 here, I get some V x. The ratio of V x to V 1 in this circuit is exactly the same as let us say I short circuit this and I apply a current source over here, I x hat, and I find I 1 hat. I know that V x by V 1 in this circuit will be exactly the same as minus I 1 hat by I x hat. Okay. Now, why is this approach advantageous at all? It looks like I am going around in loops, I mean making the problem only more complicated. The point is, let me now take the case where V 2 is acting by itself. I have set V 1 and V 3 to 0, okay, and I can calculate V x. Now, I also know that the reciprocal case for this is, again, instead of going from V 2 to V x, I can go from I x hat to I 2 hat over there. Okay. The point is, this network is exactly the same as before. I am simply calculating I 2 hat. Previously, I calculated I 1 hat over here. And now, you can easily imagine that if I had only V 3 acting here and the other two were set to 0, the reciprocal case of that would be when I have I x hat here and I simply calculate I 3 hat. Okay. So, this network, the reciprocal network, remains exactly the same for all these three cases. Remember, I have three sources here V 1, V 2, V 3. I can do superposition by taking one of them at a time. Each one of them will give a different network. By different network, I mean, in one case V 2 and V 3 are replaced by short circuits, in the other case V 1 and V 3 are replaced by short circuits, and in the third one V 1 and V 2 are replaced by short circuits. Okay. Now, if I take the reciprocal cases for each of these three, the network is exactly the same. I apply a current from this side and I simply have to calculate these three currents. Okay. So, and that is very easy, right. So, for this reciprocal case, I know that V x by V 2 exactly equals minus I 2 hat by I x hat. Okay. Now, what do I do with this? So, this is the reciprocal case and I have to find I 1 hat, I 2 hat and I 3 hat over here, and I have this current I x hat injected from this side, and this is just current division, right, into 3 resistors or 3 conductances, and that is very easy. I know that I 1 hat is simply minus I x hat. I know that I x hat is injected in this direction. So, the actual current in R 1 will be in the opposite direction in terms of I x hat. So, I will have minus I x hat times the ratio of conductances. This is the current divider case. So, G 1, which is 1 by R 1 divided by G 1 plus G 2 plus G 3. Similarly, I 2 hat will be minus I x hat times G 2 by G 1 plus G 2 plus G 3, and finally, I 3 hat would be minus I x hat times G 3 by G 1 plus G 2 plus G 3. Okay. And if I look at the coefficients, minus I 1 hat by x hat, this is what I want, right. This is V x by V 1, minus I 2 hat by x hat, which is V x by V 2, and minus I 3 hat by I x hat. Okay. So, these ratios would be simply what is inside this circle. Okay. This one and that one. Okay. So, in my original circuit now, okay, I have got to do superposition, and that is quite easy. V x is simply contribution from V 1, which is V 1 times the ratio which I wanted, and that ratio is nothing but G 1 by G 1 plus G 2 plus G 3, okay, because this minus I 1 hat by x hat is nothing but V x by V 1 when V 1 is acting by itself. Similarly, minus I 2 hat by x hat is when V 2 is acting alone, and finally, minus I 3 hat by x hat is when V 3 is acting alone. Okay. So, V x would be in this case V 1 times G 1 by G 1 plus G 2 plus G 3 plus V 2 times G 2 by G 1 plus G 2 plus G 3 plus V 3 times G 3 by G 1 plus G 2 plus G 3. In other words, V x in this case is V 1 times G 1 plus V 2 times G 2 plus V 3 times G 3 divided by G 1 plus G 2 plus G 3. Okay. So, quite a simple formula, and you can generalize this if you have a number of more sources. So, let us say I connect n of these together, V n and R n. I will simply have to continue this formula V n G n, and in the denominator also all the way to G n. Okay. So, this is what we will have. Okay. Now, like I said, you can derive this in many ways. In particular, I would encourage you to try and derive this by using Thevenin and Norton equivalents suitably, but this is one way in which you could use reciprocity, right. My original circuit had multiple sources, and I wanted to calculate this particular output. Instead of that, I can turn this around and use reciprocity. I connect a single source here, and after that it was very easy in this case, especially because it was just a current divider. I had to find all these branch currents, and each one has some ratio to the original current, and I multiply all these voltages by corresponding ratios to get the final voltage. Okay. So, that is how you can use reciprocity in this case and also in many other cases. Okay.